In the world of the superhot, plasma is about as hot as it gets. It's the stuff that stars are made of. In fact, it's the stuff that 99% of all visible matter in the universe is made of.
We think of plasma as the fourth state of matter, after solids, liquids, and gases.
This fourth state, also referred to as ionized gas, occurs when gas atoms become superheated, causing one or more of their electrons to be stripped away. The freed electrons move about rapidly, making the superhot plasma electrically conductive. A common visual characteristic of many plasmas is light.
The temperature inside of here might be of the order 5,000 or 6,000 degrees F. Now, there aren't a lot of particles inside of here. So even though 5,000 degrees F sounds like a high temperature, I can still touch this, and it's not hot. And that's because the number of particles in here is relatively low.
Increase that density of particles, and you've got that big hot ball of plasma known as the sun. The sun's temperature varies greatly from the surface at about 10,000 degrees Fahrenheit to its core of roughly 25 million degrees Fahrenheit. On Earth, we've learned to harness the energy of high-density plasmas to create the heat for plasma cutters and welding arcs. And light from low-density plasmas glows in plasma televisions and many of the lights around us. Fluorescent and neon lights are really plasma lamps. They're considered low-pressure arc lamps with two electrodes separated by gas. When charged, the gas turns into illuminating plasma. Oak Ridge National Laboratory has the most powerful high-intensity DC arc lamp in the world, capable of heating a surface at a rate of over 1 million degrees per second. That means it can process a variety of materials in a short time.
Take metal powders on coatings and directly fuse them, turning them liquid, melting anywhere up to, say, 6,000 to 7,000 degrees Fahrenheit. We basically have no temperature limitations with this type of technology.
Inside this very powerful, very bright, high-temperature arc lamp swirls argon gas within a quartz tube, sealed by two electrodes on each side. When a strong arc of electricity travels between the electrodes, it strikes the argon atoms, generating an intense radiant heat similar to that of the sun. To keep the lamp cool, jets of highly pressurized, deionized water coat and spiral around the tube's inner wall. The lamp takes the radiant energy of the arc and directs it onto whatever material is being processed. Superhot plasma isn't just handy for high-tech manufacturing. How about high-tech garbage disposal? It's used in Japan and US military bases like Aberdeen Proving Grounds. Companies like StarTech Environmental have created machines called plasma converters to break down all types of waste materials.
Plasma converter employs a very high temperature plasma at about 30,000 degrees at atmospheric pressure. And no matter how hazardous the material is that we have, none of their molecules could withstand that heat. So the plasma breaks up the molecules into the constituent atomic elements.
The system produces more energy than it consumes. The byproducts of the process include hydrogen and other gases that can be used to produce electricity for the converter, plus extra energy to be fed back into the grid. Additionally, the converter creates an obsidian-like stone with potential for use as a road base. Take the 30,000 degrees in the converter, make it over 3,000 times hotter, and you've got the temperature needed for the most impressive and hottest use of plasma, the holy grail of energy, plasma fusion, the process that powers the stars. Harness it, and we could have an inexhaustible supply of clean energy. For fusion to occur, two light atomic nuclei, like the hydrogen isotopes deuterium and tritium, must join together to form a heavier nucleus, like helium. Some matter becomes energy in the process, according to Einstein's famous formula, E equals mc squared. But getting there isn't easy.
Because the particles are positively charged and it takes a lot of energy to overcome that mutual repulsion force, we heat it up to very high temperatures, 200 million degrees Fahrenheit or more, to achieve fusion-relevant temperatures.
While only a few machines have sustained these temperatures for more than 5 seconds, no fusion reactor has been able to produce as much energy as it consumes. General Atomic's D3D National Fusion Facility in San Diego, California, is one of several international facilities researching ways to achieve sustainable fusion energy. Someday, this limitless energy could heat water into steam, which could turn massive turbines to power the world's cities. Scientists are betting on a donut-shaped machine like this, called a tokamak, which confines ultra-hot plasma with magnetic fields.
So I'm standing here in the machine hall of the D3D National Fusions Facility at General Atomics. Below me is the tokamak itself. This is the largest tokamak in the United States.
In order to create fusion in a tokamak, plasma must be heated to at least 8 times the temperature of the sun's core.
Because the sun has a very strong gravitational pull. It condenses matter in a very small area, and so 25 million degrees Fahrenheit is sufficient to generate large amounts of fusion energy. On D3D, where we use magnetic confinement isn't nearly as good at holding particles close together. And so to compensate for this, you have to go to much higher temperatures.
So what does it take to heat something hotter than the sun?
First, to get this up from a normal gas to about 100 million degrees Fahrenheit, is we simply induce a current through this plasma. But to get fusion to really occur, you've got to get up to something like 200 million degrees.
This is where other energy sources take over. D3D utilizes very powerful microwaves, high-energy particle beams, and high-frequency radio waves.
With these 3 heating systems on D3D, we have achieved temperatures close to 600 million degrees Fahrenheit.
To feed the fusion reaction, General Atomics continually fuels the tokamak. One novel approach that also increases the plasma's density is injecting deuterium ice pellets directly into the hot plasma.
We like to call this a snowball in hell because it's a 4-degree Kelvin pellet being injected into a tokamak plasma that is close to 200 million degrees Fahrenheit.
General Atomics and other research labs have created fusion reactions, but the goal of a self-sustaining reaction is still very elusive. Maybe ITER will change that. Currently under construction in Cadarache, France, the ITER tokamak is a historic collaboration between the European Union, Japan, the United States, Russia, China, the Republic of Korea, and India.
So here we have more than half the population of the world working together to solve a global problem. This, in fact, is more important than science.
When completed, ITER will be over 4 times the size of the current largest tokamak, JET, located in England. It will also have a magnetic field over 10,000 times that of the Earth's.
The facility is quite large, with the plasma residing in this area. If you look at the volume of that plasma, it's about 800 cubic meters, which in down-to-earth terms is about the volume of the water in an Olympic swimming pool. So the bigger the plasma, the bigger power.
Construction of this supersized tokamak should be completed by 2018. But don't expect to see a self-sustaining energy-producing fusion reaction for another 10 to 20 years beyond that. If it can be achieved, the benefits will be well worth the wait.
This would be able to produce enough energy for humankind for millions of years. It does not pollute with any carbon dioxide, no greenhouse gases, and no high-level radioactive waste. So we think that's sufficiently attractive that it's worth dedicating our lifetime to study.
While superhot plasma may someday provide us with clean, limitless energy, our homes are filled with another kind of superhot, a potentially dangerous kind. In 1995, a tokamak at Princeton University produced a world record plasma of over 900 million degrees Fahrenheit for half a second. That's over 30 times the temperature of the sun's inner core. Superhot will return on Modern Marvels.